Okay, ladies and gentlemen, welcome to 7.1. This will be solving systems of two equations. You might remember this a little bit, sounds a little familiar. This is kind of an Algebra 1. We would initially teach you guys this in Algebra 1 with linear functions, but we're going to move beyond linear functions, look at obviously nonlinear functions, and look at it basically exactly how we looked at it in Algebra 1. So this is going to be kind of a brief video of just a refresher on how to do this. All right, so there are two different ways basically that we use. We use substitution or elimination. You might recall a little bit of that. There is a graphic way to do this as well, but it's not harder. It's just a little bit more not user-friendly, I think. All right, so let's look at by substitution. So this is the first one. Some people prefer this one over elimination, but it's really important that you know how to do both. So here's our first example. There's really not going to be much words outside of the examples today. So for substitution, let's get a good pen here. For substitution, what you want to do is you want to solve one of the equations for one of the variables. Well, in this first one, doesn't matter which one you use, I just look at this and I go, if I tried to solve one of the variables for the second equation, I'm going to create fractions, and I don't really want to do that. But if I solved for y right here, I would add y to both sides. So I'd add y, and I would subtract 10 and minus 10. So I would get the equation y equals 2x minus 10. Now that I have y equal to something, I can take this something and I can substitute in for wherever I see a y in the second equation. So I get 3x plus 2 times whatever y was in the up here. So y up here is 2x minus 10, and this is equal to 1. And this becomes pretty simple now. We can say it's 3x plus 4x minus 20 equals 1. We can say 7x is equal to 21 when I add 20 to the other side. X is 3. But some people forget that that's not the question being asked. They actually kind of forget what this whole process is. We are trying to find an x and a y that makes both of these a true statement, the same x and the same y. And we'll think about this graphically a little bit later, but it's basically a coordinate that they both share, or more commonly known as the intersection point. So if x is 3, I say, okay, if x is 3, I know I can find y by doing this. I can say y is equal to 2 times the 3, because it was 2 times x here, minus 10. So I get y equals 6 minus 10. Y is negative 4. So the answer to my system of equations is 3, negative 4, and that would be my solution. And if we were to graph these, which we're not really going to do in this particular lesson, but if we graph this, they would intersect at the point 3, negative 4. All right, so that's the first example with substitution. However, this is a linear problem. They're not all going to be linear. So you'll look at this example coming up here. I want to find the dimensions of a rectangular garden. Oh, that was supposed to say that. That has perimeter 100 feet and an area of 300 feet squared. Now, this is a particularly good problem because this could be a real-world situation. You want to know basically how big of a garden this is. And when you get to calculus, you're going to be calculating a little bit differently. What would be your maximum area given a certain perimeter? But it's the same kind of idea. So let's just kind of, with word problems, as always, we kind of just say, okay, what kind of picture do I have? Well, I have x and I have y. Here's my garden. And because it's rectangular, I know this is x and this is y. So if I was to find perimeter, perimeter is what, 2w plus 2l. Well, I have different variables for that. I also have an area. Area is width times length. Well, let's plug in the variables that I'm actually using here. Let's use x and y because I kind of like using x and y. I know my perimeter is 100. And my width is x, sure, I don't care. And my length is y, so I get 2y. And then I have area, which is 300, equals x times y, or xy. Now, I kind of like to simplify this particular equation here, the perimeter equation, saying if I divide everything by 2, I can say it's actually 50 equals x plus y. And since we're solving with substitution, this one doesn't actually work with elimination. You have to use substitution. I would get y by itself, or x by itself, doesn't matter, but in this case, 50 minus x. I'm then going to substitute that in. I'm going to say 300 equals x times 50 minus x. And in this particular case, I get 50x. That's ugly, 50x. Oh, shoot. Darn it. I just eliminated all my stuff. All right, so I had the equation 300 equals xy, and I had the equation 100 equals 2x plus 2y. So y is equal to 50 minus x. Now I can go substitute. 300 equals x times 50 minus x. And I get this. 300 equals 50x minus x squared. Oh, that means we got a quadratic function, which means we set it equals to 0 all the time. So we get x squared minus 50x plus 300 equals 0. And you should be able to understand where that comes from. This is, excuse me, this is not factorable. And if it's not factorable, you have to do the quadratic formula. Because I have this quadratic formula done for me, and because it should be a memorized equation for you, for yourself, for your own personal benefit, when you do the quadratic formula, you get x equals around 6.97, or x equals 43.03-ish. Remember, you're using the exact numbers when you do your calculations. Well, if x is these two numbers, or x are these two numbers, I guess, you can plug those two numbers right back up into here so you can solve for y. And what you'll notice that actually 50 minus 60, or 50 minus 6.97 is 43.03. And 50 minus 43.03 is 6.97, which means in this case, y is 43.03, and in this case, y is 6.97, which means your rectangular garden is 6.97 by 43.03, and if we use our feet marks, feet by feet. And if you multiply those two things together, you should probably get 300 as well. Okay, so that's a nonlinear. We have another nonlinear here coming up. Oops. Let's try this again. Play. Come on. Work for me. Here we have y equals x cubed minus 6x, and we have y equals 3x. Well, here, this is kind of nice because graphically, if you think about this, graphically, let's get my pen going on here again. Oh, my goodness. Wow, all sorts of problems today. Okay, let's try this again. If you were to think about this graphically, you would have a cubic function that looks probably a little bit something like this. You would have a linear function that comes in here like this, going through the origin, and you would see that there are actually 3 points where this intersects. Or you could have a quadratic that has a line through it, so you'd have two answers. So let's figure this one out. This one is a substitution problem. You cannot use elimination here. It does not work. But what we can say is since y is x cubed minus 6x and y equals 3x, that means technically by our transitive property of equality, 3x is equal to x cubed minus 6x. So we can say 3x equals x cubed minus 6x. Whenever we're dealing with polynomials, we set them equal to 0. So 0 is equal to x cubed minus 9x because I subtracted 3x from both sides. And we do some simple algebra. You guys are going to be happy because we're kind of a little bit back into a little bit of algebra, just some higher level stuff. And we continue factoring. And we get that x is 0, -3, and +3. But remember, we're looking for coordinates. So I plug it back into the easier equation. And I say I get the coordinate 0, 0. I get the coordinate 0, oops, sorry, not 0. I get -3 as x and -9. And I get the coordinate 3, 9. Okay, so that would be your 3 solutions. Again, kind of using substitution. I guess not kind of, it's exactly using substitution. All right, so obviously substitution, for the most part, I think is the only way you can do nonlinear systems. Some nonlinear systems you will have to use graphically, so you need to know how to use your intersection key on your calculator. If you don't, you can ask me later. But my personal favorite when we get to the linear systems is actually using the method of elimination. And problems that look like this again, so we have 2x plus 3y equals 5. And -3x plus 5y equals 21. Well, the idea in elimination is to eliminate one of the variables. And one of the nice properties here is that we could add the 2 equations together, or we could subtract the 2 equations. But the whole point of that is so we can eliminate one of the variables. But right now, none of my variables are the same. So if I added these, I wouldn't get rid of x and I wouldn't get rid of y. Same thing if I subtracted, I wouldn't get one or the other. So what we have to do is we have to manipulate the equation. I know that if I multiplied this top equation by 3, I would get a 6 right here. So let's see about this. Let's multiply this by 3. I get a 6x plus 9y equals 15. So I just multiplied the entire equation by 3. Now, the reason I did that is because I'm simply trying to get rid of the x values. You could have gotten rid of the y's by multiplying by other numbers, but with the x's, I can multiply this by a 2, and I get -6x plus 10y is equal to 42. And then I look at this in equation, and I go, hey, I have a positive 6x and a negative 6x. If I were to add these 2 equations together, the x's are going to cancel, and I get 19y is equal to 57. Well, it just so happens that 19 times 3 is 57. So now I have y equals 3, and now I need to figure out what x is. So I go back to my simpler equations. I don't need to use the bigger ones here. I say, okay, well, 2 times x plus 3 times 3 is 5. 2x plus 9 is 5. 2x is -4. X is -2. So the solution to this particular question is -2, 3. Make sure you put them in the right order. I solved for y first, so that comes second in my coordinate, and x comes first in the coordinate. All right, sometimes equations look a little bit different though, or not really different, but different types of solutions here. So I look at this equation or this system again, and I say, well, I don't have anything the same, so let's multiply by 2 so I can get double or the same x's. So here I'm going to multiply by 2, and I'm going to get 2x minus 6y equals negative 4. And my bottom equation I'm not going to do anything to, so I have 2x minus 6y equals positive 4. And you might be seeing, oh, something's weird here. That's right. But we notice here I get 2x and positive 2x, which means if I subtract the two equations, I'll get rid of my x's. So 2x minus 2x is 0. Negative 6y minus a negative 6y, oh, well, that's 0 as well. And then here I get negative 4 minus 4 is negative 8. You guys got to stop saying that's 0 because it's not. So what this is saying is 0 equals negative 8. Well, some people get really confused with this. And I basically ask the same question. Does 0 equal negative 8? The answer is no. Are they ever equal? No. So in this particular case, when you get a number equal to a different number, this is a no solution problem. And basically saying if you were to solve these equations for y and graph them, you are getting parallel lines. Parallel lines never intersect and therefore have no solution. You guys might remember this from Algebra 1. Who knows? Last type, you might guess what the next type of equation is. I look at this and I go, hey, 4x and 12x. I can multiply the top equation by 3. So I get, okay, multiply by 3. I get 12x minus 15y equals 2. And I get negative 12x plus 15. Oops, sorry, this was supposed to be 6. Plus 15y equals negative 6. I notice I have a positive 12 and a negative 12, so I'm going to add. And then you're really like, oh, wait a minute. This becomes 0. This becomes 0. And this becomes 0. So then it's saying 0 equals 0. And this confuses people even more. And I've asked this in the past. I say, well, does 0 equal 0? I've actually had people tell me no. So 0 equals 0. This is a true statement. It's always a true statement. So it's all solutions. Or in other words, infinitely many. Okay, basically saying if you solve this equation for y, this would be the first equation. And the second equation would be this. Because they're exactly the same. They intersect infinitely many times because they are actually the same equation. All right, so that's the elimination method. You're basically, like it mentions, you're eliminating one of the variables. Last thing I'm going to kind of mention is what I've been mentioning the whole time. Each of these problems, every single one of them could have been done graphically. The book likes to use the word supported graphically because it wants you to usually solve it algebraically and then support your answer graphically. It's basically verify that the answer is correct. The solution to the system, in our case, for this particular section, right now it's only 2 equations, but it could be 3 or 4 or 5 or many different equations. You could have all sorts of things. You could have parabolas intersecting with linear functions. You could have parabolas intersecting with absolute value functions. You could even technically have parabolas intersecting with cubic functions. And we actually dealt with these kind of things in like Algebra 2, which technically we used substitution and solved for the zeros rather than the intersections. But you'll see those when you get to them. We actually did one already. All right, this type of thing can be used in the real world. If you have 2 equations, you want to see your break-even point. Like if you're looking at here are your expenses are going down and your income comes up. And there's a point in time when your expenses meet your incomes, and that would be your break-even point because you're not making any money. you're spending money and making money at the same rate. But as soon as you start making more money, this is usually a time graph, and you can use this type of information to solve for how many things do I have to sell. This is how much it costs to make each piece. This is how much you make on each piece. The more you make, the more you build, the more you make. And basic economy, basic economics, or kind of. All right, so that's the extent of today's lesson. I'm putting it up super early just because some people kind of want it a little bit earlier, and I will try to put them up early. Have a good evening, and I will see you guys tomorrow.